Good morning, students. So we will begin with interfacing of ADC and DAC with microcontrollers. Now first we will look into why do we need an analog to digital converter. Whatever parameters in real world are, all those parameters are analog in nature. Okay. So the parameters that we want to measure for processing are, suppose, temperature, pressure, light intensity, humidity, velocity of wind or velocity of water, right? All these parameters, physical parameters, are analog in nature, correct? So then, so as to operate on these parameters, what do we need to do? We need to sense these physical parameters. So these parameters are all analog in nature, and we need to measure these parameters. And these parameters are sensed by sensors or transducers, right? So what does these sensors do? These sensors will sense the parameter and convert it into one electrical signal, either in the form of current or in the form of voltage. But even when the conversion is done in the form of current or voltage, right, and they cannot directly be given to microprocessors or microcontrollers, because microprocessors and microcontrollers are digital in nature. So then, in between, these analog quantities need to be converted into digital, and then can be given to microprocessors or microcontrollers, and that is where we need analog to digital converters. Is that fine? Now why do we need to convert them into digital? In whenever the quantity is converted into digital, there are only two voltage levels that need to be operated on, that is 0 volt and whatever is the VCC or the supply voltage of that particular IC. So whatever processing which is need to be done on the signal, we need to process only two voltage levels, 0 volt and 5 volt. So then the processing becomes easier, and as well as there are many techniques to process on digital data, right? Whereas in case of analog, when do we say that the signal is analog? With respect to time, if I measure that particular signal, the signal keeps on varying continuously. So suppose at time t1, the signal is showing me 2 volt. At another time interval, it will show 3.5. Next time interval, 4.6. And that is, we call it as an analog signal. Whereas in case of digital, with respect to time, if I measure a digital signal, it will show only two fixed values, either 0 volt or 5 volt. Correct. So if I think of processing on that analog signal, the circuitry needs to take care of multiple voltage levels. The processing needs to be done on multiple voltages, right? Whereas in case of digital, the processing need to be done is on only two voltage levels, 0 volt and 5 volt, right? So then analog processing becomes a bit difficult, right? So see, for example, in old days, we had those cassette recorder, cassette tape, that brown color film, right? So if I think of making another copy of that cassette, the second copy would get degraded. Whereas you look into digital circuits, CD, right? Whatever we write, it is in the form of digital. I can create exact copies of digital signals. That is, if I copy 100 CDs, all the 100 CDs will have the same quality of sound, the same quality of video. Correct. So processing on digital data is much easier and is much accurate. Whereas in case of analog, that is not the case. Signal just duplicate. So then what is done is, analog quantity, the real world signals are sensed. Those analog signals are converted into digital and then are processed by microcontrollers and microprocessors. This is the necessity of ADCs, right? Now next, whenever we talk about ADCs, what are the characteristics or what are the features that we should look upon? The first one is, what is the resolution of ADC, right? Resolution is the number of bits that we have in the digital data. That is called resolution. So analog to digital converter, one analog quantity will be converted into digital in the form of bits, binary bits. So how many binary bits is the digital data is called as the resolution. 8-bit resolution, 10-bit resolution, 12-bit resolution, right? And accordingly, whenever we refer to what is the size of ADC, we say it is an 8-bit ADC, 10-bit ADC, and 12-bit ADC. So what does that mean? The digital output that is going to be generated is in the form of 8 bits. That is 8-bit ADC. When we say 12-bit ADC, the digital output data is of 12 binary bits. Correct? 24-bit ADC, the digital output data is in the form of 24 binary bits. Right? So that's the naming of ADC. Right? 8-bit ADC, 12-bit ADC, 24-bit ADC. Now the number of digital bits is itself the resolution of ADC. Right? So the first parameter is how much is the resolution of the particular ADC. The second, what is the steps ADC? Okay, so what is the step size? The smallest change in analog input that is recognized by ADC and converted into digital is called the step size. Right. So the formula for step size is given. Step size is V reference upon 2 raised to n. And now what is V reference? V reference decides. Okay, so what is V reference? V reference defines what is the range of V in. So if I say V reference is 5 volt, it means V in can vary from 0 volt to 5 volt. If V reference is 2 volt, it means V in can vary from analog signal V in can vary from 0 volt to 2 volt. So this V reference decides the maximum limit of the analog input signal. Is that okay? And that decides the step size. So step size is V reference upon 2 raised to n. So what is n? The number of digital bits in the ADC. So if I say it is an 8-bit ADC, n is 8. And if I say V reference is 5 volt, it means the maximum analog signal that can be applied as an input will range from 0 volt to 5 volt. So in that case, what is the step size? 5 volt upon 2 raised to 8. So that 2 raised to 8 is 256, right? So 5 volt upon 256. And 5 volt upon 256 comes as 19.8 millivolt or 19.5 millivolt. Correct. So for an 8-bit ADC, 5 volt V reference, the step size is 19.5 millivolt. What does that mean? It means when analog input voltage is 0 volt, the digital output is 0000 8-bit binary. The next voltage, the next analog voltage that will be recognized is 19.5 millivolt. So after 0 volt, the next analog voltage recognizes 19.5 millivolt and the corresponding digital output is 0001. Then third voltage which will be recognized is again add 19.5 in it, a step of 19.5. It means 19.5 is the current analog voltage whose digital output was 1. The second analog voltage recognizes 39 millivolt. So 19.5 plus 19.5 is 39 millivolt. That 39 millivolt will be recognized and its corresponding digital will be 0010. That is 2. Right? So then the voltages that will be recognized are in the step of 19.5 millivolts. Then what happens with the in-between voltages? It means the voltage from within 0 volt, in between 0 volt to 19.5 millivolt, they are ignored. So if I say 10 millivolt is the analog voltage, that 10 millivolt will be ignored by the ADC. Why? Because the step size is larger than that. Correct? So that is what is called as step size. The smallest change in analog voltage signal that is recognized by ADC and converted into digital. Right? Now because of this, what happens? Whenever we go for analog to digital conversion, few of the voltages will be skipped. or ignored. Due to that, there will be error in the mean, suppose analog signal, I convert it into digital, and from digital I convert it back into analog. I will not get the exact analog signal back because of that error, because of that step size. Is that okay? The exact and the accurate analog signal, we cannot retrieve it back. Why? Because of the step size. Smaller the step size, more accurate is digital to analog conversion back. Okay, so now this step size also decides the accuracy of ADC. So one more characteristics of ADC is accuracy. Whatever digital data has been converted, how close is the digital data with respect to the analog signal? That is called accuracy. And that accuracy depends on the step size. Smaller the step size, more accurate is the conversion. Is that okay? Then how do you reduce the step size? Look into the formula. How do you reduce the step size? The denominator term 2 raised to n. If you increase that 2 raised to n, the step size will be reduced. What is n? The number of bits in the ADC. So larger the number of bits in ADC, smaller is the step size, more accurate is the ADC. Is that okay? What is another way to reduce the step size? Look into the numerator term, V reference. Smaller the V reference, smaller the step size, and more accurate is the ADC. Correct? Now, how can you reduce the V reference? So suppose whatever analog signal we are going to do the conversion, suppose the maximum limit of the analog signal is 2 volt, we should not keep V reference 5 volt. Unnecessary. Right? So whatever is the maximum limit of your V in, that should be the V reference. Why? Because reducing the V reference will reduce the step size. Correct? More the number of bits in the ADC, that will also reduce the step size. And lesser the step size, more accuracy that analog to digital conversion has. Now, there is one more term associated, and that is called conversion time. And from the name itself, on giving an analog input, after how much time you get a digital output, that is the conversion time. Smaller the conversion time, faster is the ADC. Right? So these are the characteristics of ADC: resolution, step size, accuracy, and the conversion time. Now then we will look into, so what is resolution? That n-bit ADC. 10-bit ADC means 10 is the resolution. 16-bit ADC means 16 is the resolution. And what is the step size? V reference upon 2 raised to n. Okay. So look into the table here. So when I say 8-bit ADC, how many steps will be generated? 2 raised to n. That is 256. So 2 raised to 8 is 256. These many steps will be generated, or these many digital combinations will be generated. Correct? 10-bit ADC, 2 raised to 10, 1024 digital combinations will be generated. That means that many steps. 12-bit ADC, 2 raised to 12, 4096 digital combinations or the steps. 2 raised to 16 is 65536. Right? These many digital combinations or these many steps will be generated. Then what is the size of each step? V reference upon 2 raised to n. So for an 8-bit ADC, and if I say the V reference is 5 volt, right? Then the step size is 19.5 millivolt. For a 10-bit ADC, the step size is 4.88 millivolt. For a 12-bit ADC, step size is 1.2 millivolt. And for a 16-bit ADC, look at the step size, 0.076 millivolt. So that is where you get to know, more the number of bits in the ADC, lesser is the step size, more accurate is the ADC. Okay, so that's the relation between the resolution and the step size. Now the next. We are going to look into one particular ADC, 0808. The another most widely used is 0804 ADC. Okay, so we will look into 0808, which is an 8-bit, 8-channel ADC. 8-bit means the digital output is of 8 binary bits. And 8 channel means it has 8 analog inputs. Fine. So look into the diagram at the right hand side of your screen. This particular ADC has 8 analog input channels, in 0, in 1, and so on up to in 7. So this is where you will be connecting 8 different analog signals. At a time, only one analog signal conversion will be done. So among that 8 channels, which channel conversion is to be carried out is decided by the address bits. So look at the downside, ABC. These are the 3 address bits. So mean as if like a multiplexer. So whatever number you give here in binary, accordingly the corresponding analog input channel will be selected. So if I say it is 0, 1, 1, mean channel 3 will be selected, IN3. Analog input 3 will be selected, will be taken for conversion, and its corresponding digital will be available on D0 to D7. So the digital output is of 8 bits. And how many analog input channels? They are also 8. At a time only one channel is selected. Who does that? It's that address bits ABC. A is the LSB. Now ALE, address latch enable. The purpose of this signal is whatever address you put on the address bits will be latched inside, and then the channel will be selected. So that's the purpose of ALE, address latch enable, right? And it is active high. If address latch enable signal is not given, whatever addresses you give on ABC will be ignored. Okay, so the address bits ABC and the address latch enable work in combination. Fine. Now the next, there are 3 control signals. One is SC, start of conversion, active high. EOC, end of conversion, active low. OE, output enable. So these are the 3 control signals associated with the name itself, start the conversion, end of conversion, and once the conversion is over, read the digital data with the help of OE, output enable. So these are the 3 control signals, SOC, EOC, and output enable. And the next 2 inputs, plus V reference and minus V reference. So these are going to decide the voltage limits of the analog signal. Mostly, see, your analog input signals, if they vary from 0 to 5 volt, in that case, minus V reference is grounded, plus V reference is connected to 5 volt. If your V in varies from 0 to 2 volt, minus V reference is grounded, plus V reference is connected to 2 volt. The voltage range of analog input signal is decided by plus V reference and minus V reference. If your signal is varying from minus 5 to plus 5, then minus V reference is connected to minus 5 volt, plus V reference is connected to plus 5 volt. Is that fine? Okay. And then that's power supply, VCC ground, and a clock. Now whatever clock you connect, it is at that rate the conversion will happen. Now generally, if the clock is somewhere around 640 to 740 megahertz, then we get 110 microsecond conversion time. So the minimum conversion time for this ADC is 110 microseconds. So accordingly, we select the clock. Now, I can slow down the conversion time by reducing the clock frequency, correct? But I cannot make the conversion time faster. So that there is a limitation on what clock you should connect. Connect a clock such that this ADC will get 110 microsecond conversion time. Now, the same pin diagram has been shown at the left side. Input analog signals are pin number 1, 2, 3, 4, 5, 26, 27, 28. Then the address bits, pin number 25, 24, 23. Address latch enable, right? So that's the pin diagram. So now let us look into the interfacing. Interfacing of ADC with microcontroller. Now, what all signals do we need to interface? See here. At these analog signals, we will be connecting some external analog input. This digital data will act as an input to the microcontroller. ADC, analog to digital conversion. Once the conversion is done, that digital data will be taken in by the microcontroller. Next, all these input signals will be coming from the microcontroller. So microcontroller will send start of conversion command. Microcontroller will activate ALE. Microcontroller will select the address ABC. Microcontroller will activate OE signal, output enable signal. Whereas end of conversion is active low, that will be received by microcontroller. So EOC is input to microcontroller, and data lines are also input to microcontroller. So now let us look into the interfacing diagram. ADC, see, the digital pins are input to microcontroller, where port 1. Correct. ALE is controlled by microcontroller. So P2.4 is ALE is connected to P2.4. End of conversion is connected to P2.7. Start of conversion is connected to P2.6. Output enable is P2.5. Next, the address bits ABC is connected to P2.0. So digital data is available on port 1 and the remaining control signals are connected to port 2. Fine. V reference is grounded. See here, V reference, chip select and ground are grounded. VCC 5 volt. Plus V reference is 2.56. That interfacing diagram had this voltage. What does that indicate? Whatever analog input is going to come, it will vary between 0 volt to 2.56 volt. That is the meaning, the voltage connected to plus V reference. And just for an example purpose, they have shown here a pot. It can be temperature sensor LM35. It can be pressure sensor, anything. Any sensor output will be connected as an analog input. Fine. And see the diagram here, D flip-flop has been shown and the signal is going to go for a clock. This is acting as a clock. Now D flip-flop, see the connection, Q bar is connected to D. Mean what are these? These are the toggle flip-flops. With every clock pulse, this is going to toggle. And the connection is, crystal oscillator is connected to the first toggle flip-flop. Output of first is a clock to the second. Output of second, clock to the third. And output of third, clock to the fourth. And the fourth flip-flop acts as a clock. Correct? Now, what is the frequency that is selected? Now, see your students, a single flip-flop divides the clock by 2. So if I say this is 12 megahertz, right, the first flip-flop will produce 6 megahertz because a flip-flop acts as a divide by 2 frequency divider. So 12 megahertz, output of first is 6. Now, output of 6 megahertz is a clock to the second. The output is 3 megahertz. Output of the third is 1.5 megahertz. And output of the fourth is 1.5 divided by 2 is 0.75 megahertz. So the clock frequency is 0.75 megahertz or 750 kilohertz. So that's the purpose of showing this 4 flip-flops. These are toggle flip-flops. Okay, so that's the interfacing diagram. Now, how does this ADC work? So let us look into the timing diagram. Based on this timing diagram, we will program the ADC. I mean, that is the sequence we will use to program ADC. Okay, so let us look into the timing diagram. So see here, the first signal is a clock. It means that 740 megahertz clock. The second signal is start of conversion, which is active high. And see, whatever signals are written in the brackets, they are applicable to 0804 ADC. So both the ADCs work as same. The only difference is 0804 ADC is a single channel ADC, only one analog input, whereas 0808 is 8 channel 8-bit ADC. Okay, so the bracket signals are of 0804 analog to digital converter. Okay. So now SC is start of conversion, which is active high. OE, output enable, reading the digital data. ALE, address latch enable. ADDR, it means those bits, ABC bits. EOC, end of conversion. And D0 to D7 are the digital pins, digital data lines. So see, initially, before starting anything, what is the status? Look at the very first timing diagram. Start of conversion is 0. Output enable is 0. Address latch enable is 0. Correct? Next, look at the control signals. What are the control signals? SOC, start of conversion, end of conversion, ALE, and output enable. So we need to take care about these 4 control signals. So initially, start of conversion is 0, output enable is 0, address latch enable is 0, and end of conversion is logic 1. What is the first step to be done? Put the address on the address bits ABC. Whatever channel is to be selected, place the address on those ABC bits. So this is the first thing. So place the address, wait for certain time, then activate ALE. So ALE is made logic 1, correct? And wait for certain time. Then activate start of conversion. So send an address, send an ALE, select the analog channel, and do start of conversion. Correct? So that analog quantity is taken in for conversion. So start of conversion is given, wait for certain time. After that, disable ALE. Mean once the channel is selected, that ALE is the job of ALE is done. So deactivate ALE, logic 0. After a certain time, deactivate start of conversion, because we need only one pulse to start the conversion. So after deactivating ALE, deactivate SOC. Mean the conversion has started. Okay, and now wait for the time and keep on checking end of conversion, EOC. Okay, once the pulse is gone, SOC pulse is gone, mean the conversion has started. Keep on checking EOC, end of conversion, and this is active low. So as soon as you get active low, I need to check the pulse. So I need to check falling edge as well as I need to check the rising edge. So once we get end of conversion pulse, mean the digital data is available on the pins D0 to D7. Now microcontroller should read the digital data. So the read operation is enable OE, output enable latch. So activate OE signal, wait for certain time, and then read the data. So this is where microcontroller will read the data. Once the data is read, disable OE. So this is the sequence of operations that we need to do. Okay, so let me repeat again. What is the first thing? The initial status, start of conversion is 0, output enable 0, ALE 0, and end of conversion logic 1. The next second step, place the address on the address bus ABC. Wait for certain time. Activate ALE. So ALE is made logic 1. Activate enable start of conversion. So logic 1 on SOC. Wait for certain time. Disable ALE. Disable SOC. Give logic 0 on SOC so that the pulse is gone. Right? Now once SOC pulse is gone, check end of conversion. Check the falling edge as well as the rising edge of end of conversion. Once you get the rising edge, mean the conversion is completed. You are sure digital data is available on the pins D0 to D7. To read the digital data, activate OE. So OE is made logic 1. Read the digital data. Microcontroller should read the digital data and then disable OE. Okay. So now with this, we will see a program. Write a program to convert analog signal into digital, which is connected to analog channel number 3. So we need to write a program and convert that analog signal into digital using 0808, and the signal is connected to channel number 3. Okay, so now what all operations that we saw is, right, see here, I'll go back to the timing diagram because that is easy to understand. So channel 3, so the address that I will be placing is channel 3. Okay, then we will activate ALE, wait for certain time, we will activate SOC. After activating SOC, we will disable ALE, then we will disable SOC. Keep on checking end of conversion, falling edge as well as rising edge. On the arrival of rising edge, we will enable OE. We will read the data and then we will disable OE. Okay, so let us go to the program direct. Now look at the program here. Now at the top, I have written where are those signals connected. ALE P2.4, address bit C 2.0, address B 2.1, address bit A 2.2. Now it is difficult to remember where is that signal. Is it P2.2, 2.6, 2.0? So then to remember this, in assembly program, we have assignment. We can assign names to that particular port pins. The directive is EQU, equate, and the other directive is bit, BIT. Okay, so see here, I have not written ORG. What are these? These are just name assigning name to those pins with the help of assembler directives. So port 1, what is connected? The data lines D0 to D7. Correct? The name of P1 is M data. So how do we give it? M data equate. EQU is the assembler directive. So port 1 is named as M data. P2.4 is named as ALE. So the assignment is ALE bit P2.4. P2.6, the name given is SOC. P2.7 EOC. 2.5 OE. P2.2 address bit A. So this is how we assign names to the pins. So it becomes easy to remember. Right? And then we start with the program ORG000. Okay, SJump start. Now the first instruction, see here. Port 1, the digital data is received by the microcontroller. So port 1 acts as an input pin. So the first thing needs to be done is input initialization. So what are the input signals? If you look into the interfacing diagram, that port 1 is acting as an input and end of conversion is acting as an input, P2.7. So initialize these two things as inputs. So into the program, hence MOV P1, #FF hex, port 1 is initialized as input, and set bit EOC, end of conversion, that pin is also assigned as an input pin. And also the default status of EOC is logic 1. Okay, next, what are the default status of other control signals? OE signal is cleared, logic 0. SOC is also logic 0 and ALE is also logic 0. So the first thing is initialization, assigning those pins as inputs and clearing the control signals. OE, SOC, ALE, right? Now, so what did we do? We cleared the control signals. Now what is the next step? Place the address channel 3. Place the address on these ABC bits. Look at the right hand side. ABC, A is LSB. So the channel is 3, 0, 1, 1. So clear the MSB, clear C, set bit B, set bit A. So the address sent is 0, 1, 1. Channel 3 will be selected. That is given in the program statement. So place the address on the address bits, wait for certain time, A call delay. Then activate ALE, set bit ALE, wait for certain time, A call delay. Then activate SOC, so set bit SOC, wait for certain time. Now after setting SOC, we will disable ALE. See here students, right? We place the address, wait for certain time. Activate ALE. So ALE is logic 1, wait for certain time. Activate SOC. SOC is logic 1, wait for certain time. After SOC, disable ALE. So ALE is logic 0. And then SOC is logic 0. So look at this. So clear ALE, clear SOC. Right? And now we will keep on checking end of conversion pulse. Now end of conversion, what is that? I should first find out logic 0, that is the falling edge. And then find out logic 1. Mean we have got end of conversion pulse. Right? So how that is done? See here. Right? I need to find logic 0. So until EOC is logic 1, wait in this loop. So jump if the bit is set. Wait here. As soon as end of conversion is logic 0, come out of the loop. That is how I check the first falling edge. And at the second time, I need logic 1. So till the time end of conversion is 0, wait in this JNB loop. As soon as end of conversion is logic 1, we come out of that JNB loop. Hope you all are getting me this. How is the pulse? I should first find logic 0, that is falling edge. And then I should find logic 1, that is the rising edge. So first falling edge is, if I do not get the falling edge, wait in the JB loop. As soon as that becomes 0, come out of the JB loop. And rising edge, as soon as I get logic 1, come out of the JNB loop. Hope you all are getting me this. So this is how I check the pulse. And once the end of pulse is over, activate OE, wait for certain time. Data from port 1, take it in accumulator. So the microcontroller reads the data and saves it in accumulator. Clear OE and stop the program. Correct? So one analog quantity got converted into digital and we stored it in accumulator. If I want to repeat the process, if that analog to digital conversion should happen continuously, look at the timing diagram. At the end of the timing diagram, what are the status? All the control signals are 0, 0, 0. So then when we loop, where should I loop? Making all the signals 0, 0, 0. Okay, so where should I loop? Right? Clear EOC, set bit EOC, clear OE. All this should be repeated except the first instruction, MOVP1, #FF. Hope you all have understood this, students. Okay, so that is analog to digital conversion. Right, so we will look into DAC, digital to analog converters. Now, whatever parameters we saw related to ADC, that is resolution, step size, accuracy, conversion time, all these things are applicable here also. Okay, so DAC, we have n-bit DAC, that is 8-bit DAC, 10-bit DAC, and so on, 12-bit, 16-bit, and so on. So what is resolution? The number of digital bits. Now these, it's a digital to analog converter. So digital is an input and output is an analog signal. So the number of digital input bits is the resolution. So when I say it is 8-bit DAC, 8-bit is the resolution. 16-bit DAC, 16 bits is the resolution. Correct? So when I say it is an 8-bit DAC, it means at the input. So 2 raised to 8, it means there will be 256 digital combinations at the input. And accordingly, for each digital input, there will be one analog value. So if there are 256 digital combinations, we will be getting 256 analog values. And these analog values, either it will be available in the form of voltage or it will be available in the form of current. And continuous analog voltage values gives you an analog signal. So for example, digital bits 0, 0, 0, if the digital input is 0, I get one analog value. So let us take an example of 8-bit DAC. So 8-bit DAC, what will be the step size? If the reference voltage is 5 volt, so yesterday we looked into the formula, step size is V reference upon 2 raised to 8. So if V reference is 5 volt upon 256 gives me 19.5 millivolt, the step size. So let us look into how is that step size applicable for DAC. So suppose 19.5 millivolt is the step size. What does that mean? For if the digital input is 0, I get analog output voltage also as 0 volt. If the digital input is 1, the output analog voltage will be 19.5 millivolt. If the digital input is 2, the output analog voltage is 39 millivolt. Mean the rise in output analog signal is in a step of 19.5 millivolt. Correct? Mean for digital value 0, output analog is also 0 volt. For digital 1, output analog is 19.5 millivolt. For digital input 2, output analog signal is plus 19.5, mean 39 millivolt. Correct? Digital input 3, output analog is 39 millivolt plus 19.5. So the analog voltage value is going on incrementing in a step of 19.5 millivolt. Correct? And such I will be getting 256 analog values. And when we combine them, we say we have got an analog signal. Are you getting me? Now, more the number of bits in DAC, smaller is the step size. See, us looking into ADC and we were looking into the step size formula. The same formula is applicable for digital to analog conversion also. So what did we say? Smaller the step size, more accurate is the output signal. Let it be a digital signal, let it be the analog signal. So we are looking into digital to analog conversion. So smaller the step size, more accurate analog signal we are going to get. So how do we reduce the step size? Look into how do we reduce the step size in the denominator. If we increase denominator 2 raised to n, larger 2 raised to n, smaller the step size. And what is n? The number of bits in either ADC or in DAC. The number of digital bits. So more the number of digital bits, smaller is the step size, more accurate is the conversion. Correct? And what is another way to reduce the step size is the V reference. Smaller the V reference, that is the numerator. Smaller the V reference, smaller the step size, more accurate is the conversion. Right? So the same is applicable for digital to analog converters also. Larger the bit DAC, more accurate, more number of analog values, it means more accurate is the analog signal. Right? And now the next, majority of the time, digital to analog, the output of digital to analog converter is in the form of current. Whatever analog signal is going to be produced, that analog signal is either in the form of voltage or in the form of current. Now the DAC that we are going to look, 0808 again, that DAC is, the output of that DAC is in the form of current. And then how is that output current calculated, that analog output current calculated? Look into the formula, 8-bit DAC. So the formula is I out is equal to I reference into bracket. These are the digital bits, D0, D1, D2, D3 and up to D7. These are the 8 input digital bits. And look at the formula. The LSB bit D0 is divided by a highest factor. It means the D0 bit has the lowest value. And the D7th bit is the MSB. It has the highest value. So the divisor factor is less. So whenever I need to do digital to analog conversion, suppose the digital bit is 3. 3 is 00000011. So place those digital bits here, 00000011, and see the value, what is the value of I reference. And with this formula, we get whatever digital input, we get its corresponding analog current. Fine. So the example that we are going to look, DAC example, the output of that DAC is in the form of current. Then what do we do? At that output, we connect current to voltage converter circuit. So the respective current will get converted into its voltage, corresponding voltage. So let us look into the interfacing diagram. DAC 0808 is interfaced with microcontroller. So what connections do we need from microcontroller? Only those 8 digital inputs. So the interfacing diagram of DAC, when we connect DAC with microcontroller, what connection should come from microcontroller? Microcontroller should give only those 8 digital bits that are to be converted into analog. Okay, so these are those 8 digital bits. It is connected to port 1 of microcontroller, D0 to D7, connected to port 1 of microcontroller. And the remaining signals, VCC and ground, right? And then the V reference, right? This V reference is going to decide the reference current, and the output is in the form of current. Look into OUT, that is in the form of current. And that current calculation, I out, the formula is this, right? So based on the digital combination, we are going to get its corresponding current analog value. And then this is a current to voltage converter, op-amp based current to voltage converter. And at the output of this, you will get the corresponding output voltage, right? So depending on the V reference that is connected, see here, depending on the V reference connected, this particular diagram, output is going to vary from 0 to 10 volt, right? If you look into this is current to voltage converter with a gain of 5. So in turn, it is giving you a voltage in the range of 0 to 10 volt. I mean, the point is, whenever we interface DAC with microcontroller, microcontroller should provide digital data. So 8-bit digital data. Let us look into how do we program it. Now programming is very, very simple. What are we going to do? We are going to generate 2 signals, 2 analog signals, ramp waveform, and the other program will be of triangular waveform. Now hope you all know what is a ramp waveform. Voltage goes on increasing linearly with time, diagonal line. If you plot it on a graph, how do you see a ramp waveform? The output voltage will increase linearly with respect to time. I mean, for example, at 1 second, output will be, just for example, right? For 1 second, V out will be 1 volt. 2 second, 2 volt. 3 second, 3 volt. 5 second, 5 volt. This is just an example. Whereas the digital circuits operates in microseconds. So how is the ramp waveform? It appears like a diagonal signal. And then once it reaches to the maximum limit, like in our case 10 volt, it will immediately become 0. Sawtooth. The similar name to ramp is sawtooth waveform. So let us look at the programming part. Now, programming, let us look into ramp waveform generation. So what do we need to do? Let the initial digital value send be 0, 0. So MOV A, 0, 0. Send this digital value to ADC. ADC is connected to port 1. So MOV A, hash 0, 0. And this 0, 0 digital value is sent on port 1. Accordingly, analog output will be 0. That will be available on IOUT. From IOUT, it will go to current to voltage converter, and then corresponding voltage will be available. Now, increment the value. See, it is a linear increment. So I will continuously keep on sending 0, 1, 2, 3, 4, 5, and so on to FF. And each digital will have the corresponding analog value. Since digital is incrementing in a step of 1 bit, analog signal will also increment with the corresponding steps. So increment accumulator, send it on port 1. Increment accumulator, send it on port 1, and keep on repeating this till it reaches FF. When it reaches FF, analog voltage will be 10 volt. Correct? Now, Again, after FF, when I increment FF plus 1, the value is 100. What is 1? It's the carry flag. So what is left in the accumulator? FF plus 1 is 100. 00 is left in the accumulator. It means after FF, what is sent to DAC? 00. So FF, the analog signal will be 10 volt, and immediately the next analog value will be 0 volt. And that's how I get a ramp. So increasing the value is in steps of 1 bit. After FF, it suddenly falls to 0. So that's the program for generating a ramp waveform. Hope this is understood to you all, students. Is that okay? Now, let us generate a triangular waveform. Yeah, see here. So I wanted sawtooth or the ramp. So look at the lowest waveform, the lowest one. So this is the ramp or the sawtooth. So the output voltage linearly goes on incrementing with respect to time. So when the digital input is 0, the analog output is 0. And then the next digital, and the corresponding analog, it goes on incrementing. And at FF, it will reach the maximum limit. In our interfacing diagram, the maximum limit is 10 volt. And after FF, if I still increment, accumulator will be 0 and 0 will be sent. So after FF, immediately the next value will be 0 volt. So that waveform, this drops down to 0. And then again I go on sending the digital value 0, 1, 2, 3, 4, 5 FF, and after FF back to 0. So that's how we generate a ramp waveform. Right? Now we will look into triangular waveform. In triangular waveform, what should I do? I should keep on sequentially sending the digital values 0, 1, 2, 3. That will be getting converted into analog signals. I keep on incrementing till it reaches FF. And once it reaches FF, I will gradually decrement. I will not decrement suddenly. That sudden decrement gives me ramp. Right? Whereas in case of triangular, after reaching FF, we will gradually keep on decrementing and keep on checking whether it has reached 0. Again, after reaching 0, I will increment the digital data and send it to DAC. And while incrementing, I will check whether it is FF. So that's the technique we will use. That's the logic we will use to generate a triangular waveform. Okay, students. So let us see the program for triangular waveform. ORG00, SJump next, and we start with the program. So we first send digital data 00. So MOV A, 00, and from accumulator, we send it on the port. From port, it goes to DAC. DAC will take it, convert it into analog. Then we increment the value of accumulator. And as soon as we increment, we will compare, has it reached FF? Because after reaching FF, we are going to decrement the value, right? If FF is reached, we decrement, but it has not reached FF, then we keep on incrementing. So then after incrementing, check, compare and jump on not equal, check it with FF. If it is not equal to FF, keep on incrementing. But once accumulator becomes FF, go for decrementing loop. So place that data in from accumulator into port 1 and keep on decrementing. So gradual decrement. Now when you're decrementing, check whether it has reached 0. Right? So while decrementing, till it becomes 0, keep on decrementing. So till it is not equal to 0, keep on remain in the decrement loop. And as soon as it becomes 0, go back for incrementing. Right? That's how you generate a triangular wave. So that's simple. Ramp waveform, triangular waveform, right? And now can you think of how to generate a square wave? Look here. If we want to generate a square wave, how is a square wave? We will first send digital 0. I should get 0 volt. And what is the immediate next? The maximum value. And we should keep on sending the maximum value for a certain time. Next, send the minimum value. Next, send the maximum value. Send minimum, send maximum. And that's how we will be generating a square wave. Correct? So when we start writing the program to generate a square wave, Initially, I will send digital bit 00 and we will wait for certain time. After that, I will send the maximum value FF and I will wait for certain time. So send 00, wait. Send FF to DAC, wait. And how much is the wait time? That depends on the frequency of the square wave. So if the square wave is of 1 kilohertz, it means 1 millisecond. Then half of the time send logic 0, half of the time send the maximum count. So 1 millisecond, half of the time is zero 0.5 millisecond. So 0.5 millisecond send digital 0, and for the another 0.5 millisecond send the count FF. That's how we generate a square wave. Is that okay? So here we complete digital to analog converters also. Okay, students.